All right, so let's pick up what we have left last time first. So recall last time we have considered in the end the curve shortening flow, the curve shortening flow in R2 of closed curves. Let's finish the remaining bit of that argument. So what we have concluded first by the avoidance principle, it has to have finite time singularity in R2. And we have the classification of self-shrinking curves, So by the monotonicity formula, the singularity model at the singularity, finite time singularity has to be a self-shrinker. And last time we used the classification of self-shrinker to say that in 1D, the self-shrinkers can only be spheres, not spheres, circles, or R1 up to rotations. So this is from the monotonicity formula and classification of self-shrinkers. And moreover, last time we have used the Sobolev inequality to say that the convergence to the self-shrinker is smooth. So what we mean by that is suppose without loss of generality, you can move your singular time to 0. What we mean is that T0 singular time, then there's this Ti going to 0 such that this rescaling is converged to a self-shrinker smoothly. Smoothly, but possibly with multiplicities. So the convergence smoothly and as graphs, but possibly multi-sheeted. And moreover, we have ruled out the high multiplicity last time. Either for spheres, or either for circles or the flat straight line, they cannot appear as high multiplicity tangent flows in one dimension. So the only possibility left is multiplicity 1 of the straight line or the multiplicity 1 of the round circle. Okay. Let me move this upward a bit. Can occur in this limit. All right, so we will actually see that if the limit is multiplicity 1 of the flat line, it's actually not a singular point. So in order to be singular, the only possibility is the first case. So this will be a corollary of our regularity theorem. So we will get to either at the end of this lecture or next lecture. So if R, then regular. So if it is singular, we have after passing to a subsequence, this is converging to this round circle. However, this is independent of the choice of the subsequence because the circle is rotational symmetric. So it's actually unique. So this limit is actually a full limit, independent of choice subsequence. So we see that and this gives you that embedded closed curve. So the conclusion is that embedded closed curve in R2 shrinks to a round point in finite time. So this is Grayson's theorem. Any questions with the argument? All right, so this is for R2. And I would also like to mention a bit in ambient Riemannian surfaces in this curve shortening flow case, 1D case. So this is also a theorem due to Grayson, but there's another possibility that can occur in an ambient closed manifold. In ambient closed Riemannian surfaces. Also a theorem due to Grayson. If you start from a closed embedded curve, regular smooth curve, closed embedded smooth curve, then the curve shortening flow, which is mean curvature flow in 1D, has two possibilities. Either shrinks to a round point in finite time, or there's another possibility. So gamma t is not equal to mt for every t greater than 0. And there exists a subsequence going to infinity, a sequence of time going to infinity, such that without rescaling here, is converging to a limit curve up to passing to a subsequence. And this limit curve is a geodesic. All right. So this, I will formulate this second case. The first case is the same. So when you are doing singularity analysis, you are blowing things up. So when you blow things up, you're blowing up the ambient space too. So in the limit, the tangent flow is always lying in R2 for finite time singularities. So in the second case, if it does not have finite time singularities, so this is I'll formulate this into an exercise. You can see that it's also we're not using the monotonicity formula, but we're using another monotonic quantity. The length is decreasing, and it's a similar argument to our blowing up and getting a tangent flow using the monotonicity formula. So it's left as an exercise in the problem set. Right, so let me draw some examples. So for example, if your ambient manifold is something like a torus, and you are starting to flow a embedded curve that are homologically non-trivial. So there's obstruction for it to contract to a point because it's homologically non-trivial. And so it will be stuck to go around this circle. And in the limit, so you will converge to something like a geodesic, a least length curve in this homology class. Because there's no singularity, so everything is in the same homotopy class. If there is a finite time singularity, you will run to the first case already. So there's in the second case, everything is isotopic the same for all time. And if you consider also an ambient manifold that doesn't really have homology, like an S2, you're flowing some closed curve in the embedded S2. So there are also two possibilities. Either if you are very close to the North Pole or the South Pole, or if it is small enough, then it's going to shrink to a point. Say a curve like this is going to shrink to a point, something like this. But if it is, well, in this case, there's no homotopical obstruction, but you can show that in the standard S2, if the initial curve separate S2 into two equivalent equal area regions, then gamma T is converging to a geodesic. This is actually if and only if. Okay. If it is not separating into equal area, then it's converging to some point in finite time. So this is written in the notes. So it's a simple argument using Gauss-Bonnet theorem. So I will leave the argument for you to read in the note. Okay. So there's one final thing that I want to mention for this second case before we proceed. So here we have to pass to a subsequence. So I don't think that is written in the literature, or at least I don't know whether you can have a full limit in the second case. To a geodesic. Yes. In the second case. Right. Intuitively, it should be true because this curve shortening flow has to be some sort of efficient, that if you're wiggling around different geodesics, it's not going to be very energy efficient to flow. But I don't think it's known that you can obtain a unique limit here yet. Okay. Right. So this is for curve shortening flow. And today's lecture, we are going to mostly focus on more complicated situations of singularities in the mean curvature flow. So let me conclude the cases that we have described, that the singularities are simple. So cases that singularity are simple. So in the first case, graphs, entire graphs. So if you have a entire graphical solution, we have deduced in, I think, the second lecture, that this is having long time existence. There's no singularity at all. And the next simplest case are convex hypersurfaces and embedded curves. Closed curves in R2. There are singularities, but the only singularity is when the flow becomes extinct. Right. But however, there are definitely much more complicated singularities. Even after the first time singularity, there might still be something left that you still want to continue the flow until there's nothing left. Right. So singularities after the first singular time. And the next simplest cases, we have mentioned the example of neck pinch. This is the next simplest cases that you can consider. So if you start from a shape of a hypersurface that is of the shape of a dumbbell. Sorry, there's no genus here. So it should be. So two sphere fat regions connected by a very thin neck. And after some time, it will stop being a smooth manifold. It will have a singularity here, a net pinch singularity. But you don't want the flow to be extinct because there's still such large mass left. So you want to find a way to continue the flow after this first time singularities. And to make this to make sense of this flow after singularities, so we will have to introduce ways to make sense of the flow, not in the smooth manifold sense. So if you have any questions, please stop and ask, because in this weak flow, there are several notions that are going to be introduced. I will try to minimize the introduction of new notions, just enough for our purpose of talking about the regularity theory. But if you do have any notions that you want me to clarify a little bit more, please do stop me and ask. Okay. So to flow through singularity, there are in general two ways. So the first way is through some weak flows. So you want to enlarge the space of manifolds or submanifold. So at a singular time, the evolving surface is not smooth. And you want to make sense of it in some other generalized settings. So you can view a surface as radon meshes. So this is, you can still continue to flow it in the sense of radon meshes. So this is the so-called brachyflow. And this is going to be the focus of our remaining two lectures. So you want to enlarge the space of smooth manifold because the space of manifold is not compact. And you want to enlarge it to a larger space so that it's still, when it gets to singular time, it's converging to something in a more generalized sense. So you can view it as meshes, which have very good compactness property. So at the singular time, you can view it as a measure. And this is a perfectly well-defined radon measure at the neck pinch singularity. And you can also view a submanifold or hypersurface as a set. So the space of closed set is also compact. So another way of extending the flow is to view every time slices of the flow as a level set of a function. And even if it stopped being smooth, it still makes sense as a set. So you can continue the flow as closed sets. Okay. So we will mention a little bit about this level set flow, because the brachyflow is, in a sense, related to the level set flow. Right. And apart from the extending the flow using weak flows, there's another way called doing surgeries. So you can continue the flow without getting to a singular object by doing surgeries. So when it is approaching a singular time, like the neck pinch example above, So you don't want it to really get into a singular thing. So when it's close enough, you do a surgery by cutting the neck and gluing two caps. And then you continue to flow this modified guy after the surgery. And these are called mean curvature flow with surgeries. And well, mean curvature flow with surgeries has a very good advantage that you have good control of the topology. You know how the topology is changing through the singularity. But the cases that is developed is very limited. Have control on topological change. Well, controlling topological change is important in application of mean curvature flow or other flow. Okay. But however, this is only developed for two convex surfaces. And so I want to say that so the surgery theory that the only kind of singularity models that you can actually do is to perform surgery on the singularity model modeled on the cylinder. Okay. So this is the only type of so in the two convex case, basically you are reducing it to the self-shrinker that the only self-shrinkers that are two convex is this round cylinders or the round sphere. But at the round sphere, the flow become extinct. The only case that you still have something left is the round cylinders. And this is the only case that you can actually do surgery for mean curvature flow. It's the singularity modeled on the round cylinders. And for those of you who are familiar with Ricci flow, it's actually in the Ricci flow, 3D Ricci flow case, the only kind of singularities that you can deal with and perform surgery are also singularities modeled on these round cylinders. And even for other generalized cylinders, no surgery theory is developed. So we will have to force us to continue the flow using the weak solutions. And of course, the weak solutions doesn't really have very good control on the topology because they are meshes or sets. But this is right now the only way that we can still continue the flow. Okay. And let's introduce the Brachy flow. So as we said, these are flow in the sense of meshes. And before we do that, we have to introduce the space of meshes. So we will restrict ourselves to hypersurfaces And in the measure setting, we will reduce ourselves to n rectifiable measures in Rn plus 1. So this is the space of n integer rectifiable measures on the Euclidean Rn plus 1. So a better way to look at this space, and actually for our purpose, is so I would recommend you to look at it as a one to as another space, because these two spaces are isomorphic. So can view it as so this is the space F in L1 such that F vanishes except on a countable union of disjoint C1 submanifold. And so this is the space of functions taking from Rn plus 1 to non-negative integers. So roughly speaking, this the space of integer rectifiable measures. This is in one-to-one correspondence to the set of countable union of disjoint C1 submanifold, and you associate to it a density function. This is the F is the density function that as measures they might appear as multiple sheets of a same on the same piece of submanifold, and this is in one-to-one correspondence. So the support of an n rectifiable measure is always supported on a countable union of C1 submanifolds. And you can associate to such a function space F in this function space to a element. You can associate to sorry, let me write it here. So we can associate a F in an integer rectifiable measure mu F, and it is defined by mu F omega to be the countable union of the Hausdorff measure where so F takes value ni on mi, and the support of F is the countable union. of this sequence of countable union of this sequence of C1 submanifold. So these are not very bad objects. They are just countable union of C1 submanifold. Not much singular than the actual smooth manifold. Okay. And then we can define our Brachii flow using this integer rectifiable measures. Any questions up to now? All right, so to motivate our definition of Brachii flow, we will first consider a formulation of the smooth flow that actually makes sense for measures. Okay. Consider first sigma t, a smooth mean curvature flow. So for it to make sense in the sense of measures, so you want to have some integral formulation characterization. So for any phi test functions, so you consider d dt of phi on the evolving hypersurfaces. So let's move this a little bit leftward. And this can be computed by, because it's smooth. And we have deduced the evolution of the area element before. So d over dt of phi is equal to partial over partial phi of t. This is we have made the distinction between d over dt and partial over partial t. So partial over partial t of phi plus the mean curvature vector in the product with the gradient of phi, and the evolution of the area element is the mean curvature square. So this is the formula that this is the integral form of the mean curvature flow. Right. So you can test a smooth hypersurface by any test functions. And this is the basis of our definition of Brachii flow. Definition. So we can replace the integral to be integrated using any measures, any integer rectifiable Radon measures. Okay. So the definition of Brachii flow. So we call a family of evolving integer Radon measures So every time slices are just Rodon meshes. So actually, we don't require every time slice to be integer rectifiable. So we just require to be Rodon meshes for every slice, but almost every time slice is going to be an integer rectifiable Rodon meshes. Say mu of t. And integral Brachy flow. So this is, as the name indicated, this is introduced by Kenneth Brachy. So it's called the Brachy flow, such that the following holds. Oops. So first, for almost every t, mu t is integer rectifiable Rodon meshes. And there exists an L2 vector field define mu t almost everywhere. This is going to be regarded as the mean curvature vector field. And second, for any positive test functions, phi in compactly supported test functions, and with enough regularity so that you can differentiate it, C2 is enough. And almost every T1, T2, such that T1 greater or equal than T2, the inequality below holds. So mu T2 phi minus mu T1 phi. Let's move this a little bit left. Is less or equal than T1 T2 let me move this downward to write the equation in one line. D dt phi plus minus phi h square d mu t. Right? So this is exactly the integral form that we have here. So when you integrate with respect to time t from t1 to t2, you get an equality. But here in the definition of Brachy flow, we will only require inequality here. So this is actually the natural definition in order to have the compactness property. So just like the Fadus lemma that you have in the real analysis, when you take integral convergence, you might have lower semi-continuity that the integral might drop. Okay. And this is crucial in order for the compactness theorem to hold. So you want to say that when you take a sequence of brachyflow, in the limit, it's still a brachyflow. But the limit definitely equality might fail. We will see later. So any questions about the definition?
Sorry. Are we taking a limit of the flows, like as we're blowing up, or are we just taking the limit as we take the sequences going to the singular time here?
Right. We haven't. You are taking a sequence of flow converging to a limit. I haven't talked about the compactness theorem yet. So the compactness theorem below is going to make the things that before we are taking limit to be legitimate. Okay.
This is like in the blow up procedure and stuff.
Yeah.
Okay.
So one of the most important advantage of this brachyflow is the Brachy's compactness theorem, so that you're allowed to take limit. So it's a closed, the space of flows are closed in the Brachy class of weak flows. Okay, so this is the Brachy's compactness theorem. So without the compactness theorem, then it's not that useful. And the compactness theorem only requires a very weak condition, only the mass bound. So suppose mu I t is a sequence of integral brachyflow in, say, some subset in the space-time. And such that you have a local uniform mass bound. So the supremum in I so say this is T in A, B. When you evaluate this measure on a compact subset, it's uniformly bounded by a constant only depend on this subset for any K compact subset in U. So this is the condition. Then there exists a subsequence IK and an integral brachyflow so this is the limit flow such that mu I t tends to mu t for every t under the weak star topology of radar meshes. So this is not surprising. The conclusion that you get a radon measure is not surprising because radon measures is weak compact. If you have uniform mass balance, it's weak compact. But the surprising part is that this limit is also integer rectifiable. And the second conclusion is that for almost every t, so there's some final convergence property, but we will not be able to prove this theorem because it's quite involved, and it will involve the introduction of the notion of varifold. But we actually only need to use this theorem, compactness theorem. So let's not focus on the proof. So this second part of the conclusion is actually coming from the final convergence property. So it not only just convergence as radon measures, they're actually converging as varifolds, a final convergence. Roughly speaking, it means that the tangent planes also converge in a suitable sense. Okay. There exists a further subsequence, IL, such that the mean curvature converge to the limit mean curvature. Also in the weak sense. Okay. So a few remarks. So this compactness theorem is what makes our previous procedure of taking tangent flows and blow up and taking limit flow legitimate. All right, and a second remarks that I want to make is originally Brachy's introduction of this weak sense is more general than what we are using here. We are focusing on a smaller class, which is the integer rectifiable measures. Actually, Brachy makes sense of that for general measures. But it's too large of a class for us to consider. And actually define it for general measures, general radon measures. And a third remark is about the inequality. So strict about the definition of our Brachy flow can actually happen. So there are potential mass drops for Brachy flows. Okay. So I will, in the following, I will introduce several examples to give you an idea of how singular behavior the Brachy flows can be. So the first example is about this strict inequality. So let's first see some examples before we proceed. It's an example that we have considered. It's the Grim Reaper. Right. So let's rotate it a bit. So the Grim Reaper was translating soliton. That was translating upward. Let's make it translated to the right-hand side with constant speed. So it's under mean curvature flow, its evolution is the original time slice plus t times E1. Say this is the E1 direction. So it translates with constant speed in one direction. And you can do parabolic rescaling for this sequence. Okay, so say m is mt. This is the eternal flow. It's defined for any negative time to positive time. And recall we can parabolically rescale this sequence of flows by a sequence of integers. But this time we are not zooming in, we are zooming out. We want to blow this thing down. Okay. D lambda I n, where lambda I is a sequence, this time going to 0. So recall this parabolic rescaling is defined by m. So this rescaled flow is MIT. And MIT is defined by, so you scale it down. And T over lambda I squared. So you are bringing things from infinity and bring it back to the 1 scale. Okay. And then by the Brachis compactness, so this is a new sequence of flow. So parabolic rescaling of a flow is also a flow. So you have a sequence of Brachii flow converge to a limit flow. And what is this limit flow? So this limit flow is actually having a mass drop. So m infinity t is equal to multiplicity to plane for t less or equal than 0. And mt for t greater than 0. Right, so because if you're zooming in for time negative infinity, when you are bringing things from time negative infinity and when you zoom in, so you're pressing everything down. So it's more and more like a multiplicity 2 plane. And this flow is going to escape any finite region because it's going rightward to infinity. So for any positive times, you are pushing it further away. So for positive times, it's going to, because when you're pressing down, the speed is going to be larger and larger. So it's going to escape finite region very soon. So in the infinity, there's nothing left for positive time. So there is actually mass drop when you take limit in Brachii flow. Okay. Right. A second example is you consider a shape of 2 circles connected by an interval, but these 2 circles are of different size. So if you flow it, what is going to happen? So there will be a time such that the smaller circle is going to, so these are perfectly well-defined radon measures. So they make sense in the Brachy sense. So you can flow it in the Brachy flow sense. And there will be a time that the flow become, the smaller circle shrinks to a point. So you are at this shape. And what happens at this time? So right after this time, this interval is going to disappear right away. So there will be also a sudden mass drop. And then only the larger circle left, and it will become smooth and then shrink to a round point in finite time. So what happened at this interval with an end is that you can intuitively think of it. So at this right end, the mean curvature also makes sense, but this mean curvature is actually equal to infinity. So it's like a delta function because it has a boundary here. So the mean curvature is going to be a delta function supported on this boundary and pointed leftward. And it is equal to infinity. So the speed is equal to infinity, which makes the interval disappear right away because it moves leftward with infinite speed. This is some kind of behavior that can happen in Brachy flow. And so this is also due to the definition of Brachy flow. So if mu t a Brachy flow, then mu t, you can chop it off at any time you like. And then just make it 0 because it's defined by inequality. So this is perfectly satisfying the Brachy inequality. Okay. This is something called gratuitous vanishing. So this is some sort of behavior that is annoying in Brachy flow. We don't really want this to happen because you're just forcing it to disappear at a certain time. But this is a disappearance that without no reason. So we will in the second half of this lecture, we will construct Brachy flow, and the Brachy flow that we constructed, starting from a closed surface, is not going to have this we call it gratuitous vanishing. It can have mass drop, but it's not going to be like this gratuitous mass drop. So for example, if you're flowing a smooth surface, you don't want it to, it's still smooth, you don't want it to just throw it away after some time. You want to continue it. So, and this leads to, okay, so it's already 1 hour. So let me take a break, a 2 minutes break before we continue. And I'm going to take a picture of the attendance, which is required. So let me know if you have any questions. No questions? Okay. So let's start at 11:40. So a brachyflow. Okay, so let's continue. So given these examples, this leads to a property of brachyflow, which is very obvious. It's highly non-unique. Because just like this chopping off at any time. So the evolution of brachyflow is non-unique. Well, this chopping off might not be a good enough example because it's gratuitous vanishing. So let's see some more fundamental non-uniqueness that it can happen. This is more fundamental than just chopping it off at any time. Okay. So for example, you can consider the crossing. So there are two legitimate evolution. So you can view this crossing as a union of two wedges, but there are two ways of looking at it. You can view it as a upward and downward wedge. So you can evolve it so they become disconnected and continue to evolve. But there's another evolution that you can view it as a left edge and a left wedge and a right wedge, so that it disconnect in another way and continue to flow it. So both of these are not having mass drop in this case, but they are both legitimate brachyflow. These are more fundamental non-uniqueness. So you might want to say that this is not smooth. So there actually are smooth initial surface that have non-unique. So it's a more involved construction due to Brian White. So the non-uniqueness is really a very fundamental issue. And in general, there's no satisfying criteria for this uniqueness property, and also for the mass drop property. So let me mention a few hard conjectures in this open questions in these issues. So that the first is so the smooth initial surface that are constructed by Brian White is not genus 0. So the conjecture that he made is the evolution of a topological sphere in R3 has unique evolution. So it is well posed. And it is already known that in the mean convex case, you can associate to it a canonical evolution. So modulo those gratuitous vanishing, you can make sense of a canonical evolution that's really the one that makes sense, except for those gratuitous vanishing. Right. And another question is what conditions can exclude mass drop? So this is also excluded for mean convex flows. For mean convex flows, it is known that the Bragg inequality is actually an equality. No mass drop. But this is not a necessary condition. So this mean convex case is due to Metzger and Schultz. Okay. So there are really very weird things that can happen for a Bragg flow as a measured theoretic flow. Right. But okay, so we have talked quite a bit about Bragg flows, but we haven't talked about whether it actually exists or not. And we can actually construct Bragg flows starting from any initial hypersurfaces, closed initial hypersurfaces. And it's actually having a little bit better property. So it's actually not going to have the gratuitous vanishing. So the next thing we're going to talk about is existence of Bragg flow. So this is not the only way of constructing Bragg flow. There's other ways too, but we'll just show you one way. Regularization. Okay. And for the elliptic regularization construction, we are going to construct the Bragg flow as a sequential limit of smooth flows. Using the compactness theorem, you can extract subsequence. So every one in the sequence is going to be smooth, but the convergence might not be smooth. So smooth guys converging to possibly singular guys in the limit. And for this Bragg flow constructed from the elliptic regularization, the Bragg's regularity that we're going to prove is going to apply in this constructed flows. Okay, so to do this, we have to recall a question, a problem in the in the second problem in the problem set. So again, it's the translating soliton. So this example appears a lot. We call in problem 2 a translating soliton. So we see that a translating soliton of a mean curvature flow actually appear as a critical point of some functional, which is given by the problem 2. So we consider upward translating soliton. So let's consider sigma m plus 1 dimensional in Rm plus 2. So notice that we have, so previously we are considering mean curvature flow in Rm plus 1. Here we raise 1 dimension higher. There's a reason for this, because we'll see later. So after taking the limit, you obtain a Bragg flow in a higher dimension that actually splits off a line. So when you modulo that splitting direction, you get the mean curvature flow, a Bragg flow in a lower dimension. Okay. So upward translating soliton. So this is sigma m plus 1 t is equal to sigma with speed 1. So it's translating upward in the em plus 2 direction. Okay. So this is plus. And from problem 2, sigma m plus 1 is a critical point of the following functional. X m plus 2 coordinate function. Okay. All right, so let me know if you have any questions or confusions that want me to clarify, okay? So if you have a translating soliton, which is, okay, so there's a typo here. This is plus t times. So the t slice is translating upward by t unit. This is speed 1. So given a translating soliton with speed 1, you can rescale it so that it can have higher and higher speed. So with speed lambda, well, by scaling, you can see that it's actually a critical point of a scaled functional. Plus lambda t e m plus 2. The speed is lambda and is a critical point for f lambda. So we will use this if so this is a perfectly smooth mean curvature flow in a higher dimension. And it is eternal, coming from time negative infinity to time positive infinity. Okay. So now we want to construct. Now go back to the lower dimensional. Now for any initial surface. So this is lying in m+1. So go back to the lower dimension. So we want to embed this into the height x m+2 equal to 0 slice of the m+2 dimensional space. So we put it, say this is m+1, and you have this, this is your m0 that you want to construct the evolution starting from this initial surface. And this is the m+2 direction. What you do is you solve the minimizer problem. Solve the minimizer problem for the functional f lambda with boundary condition. With boundary condition m0 cross the 0 time slice. So you want to find a hypersurface in the m+2 dimension such that its boundary value is this m0 in the height 0 slice. So sigma lambda sub lambda is m+1 dimensional manifold. Okay. So we see that because it's if it satisfies this minimizing problem, it's a critical point. So if you evolve sigma lambda by mean curvature flow, is sigma lambda plus T lambda E m+2. So it's translating upward. So this is a perfectly mean curvature flow for each lambda. And what you do is you use Brocchi's compactness theorem to pass through a limit. So obviously it applies to the sequence of flow. So you need to check that there's uniform, locally uniform mass bound, but this is guaranteed by, so the total mass, because it's a minimizer, mass of E lambda is bounded by the solid region that is enclosed. So this solid region. So this minimizer is but because it's minimizing, it has to be smaller than this competitor. So you have a uniform mass bound. So the Brocchi's compactness theorem is applicable. So this sequence by compactness, by Brocchi's compactness theorem. This sequence of flows, sigma lambda T, is converging to sigma infinity T. as brachyflows in Rm plus 2. So remember our goal. Our goal is to find a brachy evolution of this lower dimensional M naught. How do we extract this evolution out of this limit flow? So claim the limit flow split of a line in in the EM plus 2 direction. So by Brachy's compactness theorem, you might have to pass through a subsequence of choice of lambda. So lambda I. All right, so the claim is that this limit flow is a splitting of a direction, splitting of a line in this EM plus 2 direction. So let's see why. So say you have a limit flow and you pick a time slice, say T naught. And you translate it upward, say any T naught S in R. Okay. So this is equal to the limit lambda I go to infinity. For these sequences. But recall that for each lambda I, this is a translating soliton, translating upward. So you can change the shift upward in space by a shift in time. So this is translating upward by speed lambda. So when you translate upward, it's actually the T naught plus S divided by lambda I slice. So this is because it's a translating soliton upward. Okay. Now you pass lambda I to infinity. You get the limit flow. When you pass to infinity, this is S over lambda I is converging to 0, 2. So which means that the translating upward by any S unit is equal to the untranslated one. So that's. So it actually splits off a line. And of course, the initial surface. So recall that this is your M naught, and you are solving this E lambda. So after you pass your lambda I, possibly to a subsequence to the infinity, you will have initial data in a higher dimension, but it splits off a line. Okay. It's going to be the initial data is exactly M naught cross a line 2 in the in the cross the line in the n+2 direction. This is not a circle, any initial surface. So after modulo this splitting direction, we obtain a brachyflow in Rn+1. So this is the dimension that we want to consider, starting from M naught. Okay. So this is the intuitive idea that how you construct the brachyflow. Well, this is legitimate using the Raki's compactness theorem after passing to a subsequential limit in the measure theoretic sense. Okay, so there are 25 minutes left. Not sure if I can get this done. So I want to explain a little bit why this is called elliptic regularization. So it's not obvious that you are regularizing anything here because these are geometric intuition and measure theoretic limit. So another viewpoint. So it's actually the origin of the idea of this elliptic regularization is in the setting of PDE. So you're actually regularizing a partial differential equation when you are doing this. This is due to the Evans-Brock and Chen-Giga-Goto. So this is from the level set flow. So level set flow is the origin that this elliptic regularization is originating from. Okay. So I will be a bit sketchy here. So to just show you the idea, how this PDE is regularized. Okay. Because we don't really have much time here. All right, so so this viewpoint is that we view the evolution at time t slice to be this gamma t to be the nodal set of a continuous function. And this function satisfies a PDE. Satisfying a degenerate parabolic PDE. So because it is degenerate, that's why we want to regularize it to be a uniformly parabolic in order to get solutions. Okay. Satisfying the degenerate parabolic PDE. dt of v is equal to so this is the PDE. When you expand it out, as we did in the first lecture. You have delta ij. Okay. So don't be scared by this equation. So the deduction of this equation is quite simple, just by implicit function theorem. So you want to view this as a level set. So recall that the mean curvature flow is what? Is the speed equal to the mean curvature vector. And the mean curvature vector is equal to the divergence of the normal. And divergence of the normal for a level set is grad v over norm of grad v. So and this should be equal to the speed by the mean curvature flow, so dx dt. But by implicit function theorem, so dx dt is equal to dtv divided by the derivative in the spatial direction, right? So this is the gradient. After you multiply the gradient to the right-hand side, you get this equation. Okay. So this is the roughly how you deduce the level set flow equation. And obviously this is degenerate because so a priori, we don't have gradient bound. So so this coefficient can actually degenerate to 0. And the idea is to regularize it, to add something to make it uniformly parabolic. Okay. So we want to approximate this v by v lambda. So again, coming from the translating soliton. So recall, say, a translating soliton. So we want to write this a sequence of translating soliton as the nodal set of a function v lambda. We want to use the function v lambda to approximate our limit function v. Okay. E lambda. This is equal to, if you write it as a graphical equation, so xn plus 2 is equal to the graph of a function u lambda. As local graphs. Then you can write this E lambda t as a level set flow too. So E lambda t is actually equal to V lambda xt equal to 0 as level set of V lambda, where V lambda is V lambda x1 xn plus 1 xn plus 2 t is equal to So this is obvious because as a translating graph, you know that because on E lambda you are translating graph, so the xn plus 1, xn plus 2 direction is u lambda. So there's a typo here. This is divided by lambda. It's u lambda plus lambda t. So in the xn plus 2 direction, the time t slice is equal to, you translate the original graph upward by t times the speed lambda. So after you rewrite it, you get this nodal set expression. So which means that if you look at this equation, if you look at this function, xn plus 2 divided by negative lambda, it behaves like the t variable. So if you press down the xn plus 2 direction by lambda and you add a negative sign, then this coordinate function after change of variable should be behaving like t. And after this pressing, you should expect that passing to a limit, then you should obtain a space-time track of the flow. So let me make this precise. So define the press down. E tilde lambda. E tilde lambda is just the lambda that you press down by lambda, okay? And then taking a negative sign. Such that x1, xn plus 1, and you take negative lambda t. This is in sigma 0, the unscaled one. So the time 0 slice of the unscaled lambda. So E1 at time 0 slice. So if you draw a picture, this is E lambda, the original translating graph. You just press it down in the xn plus 2 direction by lambda. Okay. This is the graph of U lambda. This is the graph of U hat lambda. So since U lambda is the level set itself, so you can write U hat lambda as a level set 2. After you press down, it's just a matter of change of coordinate, change of variable. Where V lambda hat is equal to U lambda. And U lambda, you can denote it by U lambda hat. U lambda pressed down by lambda, you can denote it by this lambda hat. U lambda hat. Okay, so so now we can see why the equation is regularized. So since U lambda is a translating soliton, So the equation for the translating soliton is deduced in problem 2. I just write it down. So it satisfies delta ij minus 1 plus grad u lambda. This is a square. This is equal to 1. And after this rescaling, because u lambda head is a rescaling pressed down by u lambda, so the gradient scale correspondingly to. So u lambda head satisfies this is lambda square lambda square okay. So after you take out this lambda, this is equal to 1 over lambda square. Now this equation is becoming more like the level set flow equation. If you recall what the equation is like before. So this is head. So so because v lambda is equal to v hat lambda is equal to u hat lambda plus t. So the derivative of v in t is equal to 1, and derivative of the spatial derivative of v lambda are exactly the spatial derivative of u hat lambda. So thus we have delta ij minus v lambda hat v lambda hat equal to dt of v. So if you recall the definition of the level step flow, the only difference is that we have this extra term, and this extra term is the one that is making the equation uniformly parabolic. Right. So this is uniformly parabolic because the coefficient is the diagonal coefficients are greater than 1 minus this thing, which is if computed, this is lambda, strictly greater than 0 for any fixed lambda. But of course, in the limit, you let the lambda go to infinity, right? So by letting lambda go to infinity, the equation converges to the level set equation, v infinity this degenerate PDE. So this is the idea why we call it elliptic regularization. But I want to remark that this is not the same thing as we obtain using the Raki's compactness theorem. If you are careful enough, you will notice the difference, right? So previously we are taking the Bragg flow and directly pass through a measured theoretic limit. But here we are not passing the flow to a limit or passing the level set to a limit. We are passing the defining function to a limit. So V lambda is the defining function. So we are passing this defining function and the equation is satisfied to the limit. A priori, we don't know that the level sets of V lambda is converging to the level set of the V infinity. That's something we don't know. And they may well be possible that they're different. There are examples that in general, they are different. Okay, so the level sets of V lambda might not be converging to level sets. And how do we define the level set flow? So you go back to this defining function and then pass the defining function to the limit. And the level set flow is defined to be the nodal set of this limit function. Defined to be the level sets of V infinity. And of course, it's a very technical process to what do you mean by passing this defining function to a limit? It's in the sense of viscosity sense. We won't be able to talk about that, not even a little bit right now, because it's very technical stuff. But this is the intuitive relation for this elliptic regularization. Okay, I think we control time quite well today. So so I'm going to pause here for today, and there are still 4 minutes. Please let me know if you have any questions or confusions. Let me stop recording for now.